Welcome to section 4.4. Today we're going to talk about coordinate vectors. So here's what a coordinate vector is. You take a basis for a vector space, and if you have a basis, every vector in the vector space can be written uniquely as C1, B1 plus ... Cn, Bn. So you can write every vector as a linear combination of your basis vectors. The coordinate vector is simply the vector of coefficients, the C1, the C2 through the Cn. So this is our coordinate vector, and the notation is the coordinate vector, you draw the vector and then put square brackets around it and a b below, meaning relative to the basis you've chosen. This gives you a mapping from the vector space to Rn. Every vector x in the vector space gets mapped to a coordinate vector xb, which lives in Rn. So a little confusing, but I think with some examples, you'll be like, oh yeah, I get it. Okay, first example. The standard basis of P2, which is the set of polynomials of degree less than or equal to 2, is 1t and t squared. All right, so we want to find the coordinate vector of this vector P, which is a polynomial, relative to the standard basis. So what we need to do is write P as a linear combination of 1t and t squared. So P is 2 times the vector 1 plus 3 times the vector t plus negative 1 times the vector t squared. So P sub b, the coordinate vector, has 3 entries, and it consists of the coefficients 2, 3, and negative 1. And it lives in R3. So we have a vector P, polynomial in P2, and we can send it to its coordinate vector in R3. Let me do one more example like this. Suppose Q is the vector, t plus 2t squared. Well, that's the vector 0 times 1 plus 1 times t plus 2 times t squared. So the coefficients are 0, 1, and 2. So the coordinate vector for Q would be 0, 1, and 2. So for polynomials, you can really just read the coordinate vector right off of the polynomial. You just look at the coefficients, and those will tell you what are going to go into the coordinate vector. All right, let's do another example. Find the coordinate vector of x equal negative 5, 2 in R2 relative to the standard basis of R2. So the standard basis of R2 is just E1 and E2. And there they are. Okay, so x is negative 5, 2, which is negative 5 times 1, 0 plus 2 times 0, 1. This is E1 and that's E2. So the coefficients are negative 5 and 2. So x sub b is the vector negative 5, 2. You might say, hey, that's what we started with. That's equal to x. And you're right. If you take a vector in Rn and you find the coordinate vector with respect to the standard basis, you're just going to get that vector back again. All right, let's do another one. The standard basis of M22, that's a set of 2 by 2 matrices, is given here. We want to find the coordinate vector of this vector x, which is a matrix, relative to the standard basis. So we have to write x, 1, 2, 3, 4, as a linear combination of the 4 vectors in that vector space. So that would be 1 times the vector 1, 0, 0, 0 plus 2 times the vector or matrix, whatever you want to call it, 0, 1, 0, 0. And then we want a 3 in the bottom left spot, so we'll go 0, 0, 1, 0. And finally, a 4 in the bottom right spot. So XB actually lives in R4. All right, if there's 4 basis elements, XB will be in R4. If there's 2 basis elements, XB will be in R2. If there's 3 basis elements, like our first example, XB will be in R3. So in this case, we have 1, 2, 3, 4, because those are the coefficients in our linear combination. All right, and you can do these in your head. In general, if X had been A, B, C, D, the coordinate vector for X would be A, B, C, D. All right, so let's see how to go back and forth between X and XB. There are 2 directions, one's easy and one's not. So here we have a basis of R3. You can trust me, that is a basis of R3. If you put those vectors into a matrix, there would be a pivot in every row and a pivot in every column. If we're given XB and we want to find X, then given XB is 2, 1, negative 1, by definition, X is twice B1 plus 1 times B2 minus 1 times B3. So that's twice. B1 is 1, 0, 0. And then we add on B2, 2, 1, 0. And add on B3. No, subtract off B3. Sorry about that. 1, negative 1, 1. So that's the vector. Let's see. I'm adding across the top. I get 2 plus 2 is 4 plus 1 is 5. And then I get 0, 1 plus 1 is 2. And then finally, my last entry is going to be negative 1. All right, and I see a mistake I made in that top entry, and hopefully you caught it. I have 2 plus 2 is 4, but then I'm subtracting 1, so that should be a 3. All right, so there's X. Now, the harder direction, if we're given X and we want to find XB, then what we want is the coefficient C1, C2, and C3 with this equation true. C1b1 plus C2b2 plus C3b3 equals the given vector, X. All right, we know how to do that. We're just going to solve for C1 and C2 and C3 by reducing the augmented matrix. So I put in B1 as my first column, B2 as my second column, B3 as my third column, augmented with X, and I reduced to save time. And we see that C1 is 5. Sorry, that's C3. Start at the bottom. C2 is 0. And C1 is negative 2. So that tells us that XB is the vector negative 2, 0, 5. Okay, let's do a safety check. If that's true, then if I take negative 2 times B1 plus 5 times B2, times B3, 1, negative 1, 1, I should get X, which is 3, negative 5, 5. So let's just do a mental check. We've got -2 plus 5 is 3. That works. And then we've got -5. And then on the bottom, we've got 5. Check. We did it right. All right. Pause the video and try this practice problem. And then when you've finished, come back and I'll do the solution with you. All right, welcome back. If x, this is the first one's the easy direction. If we're given xb, then x is just twice b1 plus 10 times b2, which is 2, and then 6 plus 10 is 16. All right, and then the harder direction, if we're given x and we want xb, then we want to solve the equation c1b1 plus c2b2 equals x. So we reduce the augmented matrix that has b1 in as the first column, b2 in as the second column, and x in as the third column. Okay, and this will just take one row reduction, so I'll just do it here. 1, 0, 2, multiply by -3 and add. We get 4 here. So C2 is 4, and C1 is 2, and XB is the vector 2, 4. And if you're not sure you did it right, you could just check. Take 2b1, add on 4b2, and see if you actually get x, which is 210. And you will. All right. Coordinate mapping isomorphism. All right, if you have a basis for a vector space that has n elements in it, then the coordinate mapping that takes a vector to its coordinate vector is an isomorphism from V to Rn. Now what that means is that the vector space looks like Rn. If you take any set of vectors in the vector space, v1, v2, v3, whatever they do in the vector space, their coordinate vectors do the same thing over in Rn. So if a set of vectors in V spans the vector space, then their coordinate vectors over in Rn will span Rn. If a set of vectors is linearly independent in V, their coordinate vectors will be linearly independent in Rn. So some examples are P2 is isomorphic to R3. Because we take a polynomial, a plus bt plus ct squared, and we map it to a vector in R3, a, b, c. So any polynomial in P2 is equivalent to a vector in R3. M22 is isomorphic to R4, and the mapping is similar to this example we did, example C, where we can take any matrix and find its coordinate vector, and that lives in R4. All right, so let's do some examples. So what I'm going to do is I'm going to do an example with you, and then we'll pause and have you practice one. And then the rest of the practice problems, I put solutions at the end. So this video won't be too long, I hope. Okay. Just missed that. Consider the set P1, P2, P3, P4. So that's 4 polynomials. And we want to write down the coordinate vector for each polynomial relative to the standard basis of P2, which is 1t and t squared. All right, so the first coordinate vector, we just pick off the coefficients. The first polynomial is 1t, so that's got coefficients 1, 1, and 0, because there's no quadratic term. P2 has coefficients 2, 3, and 0. P3 has coefficients 0, 1, 0. And the coefficients in P4 are 3, 4, and 1. Okay, now we're going to put those vectors into a matrix and reduce the matrix to echelon form. And I've already done that. Here's our echelon form. And we don't need to go to reduced echelon to answer questions 3, 4, and 5. So the first question is, do those vectors, do P1 through P4 span P2? And so we can, now that's a problem in R3, we say, do the coordinate vectors span R3? So we're looking at pivots. We've got a pivot in every row. So the answer is yes. Pivot in every row. Okay, determine if the vectors are linearly independent by determining if their coordinate vectors are linearly independent. Well, we don't have a pivot in every column, so no, not a pivot in every column. All right, based on answers 3 and 4, do P1 through P4 form a basis for P2? No, they span, but they're not linearly independent. And for a basis, you need both. So what we were able to do is look at 4 polynomials, and it wasn't clear whether or not they formed a basis for P2. But by translating the problem into coordinate vectors and looking at vectors in R3, we could solve the problem in R3, which we're familiar with, and then go back and make a conclusion about the vectors in P2. All right. I know this video is getting a little bit long, so pause it, go ahead and do practice 1. When you unpause it, I'll solve practice 1 with you, and then you can solve the other ones by yourself, and the solutions are at the end, and if you have questions, we can Zoom about it. All right, so assuming you've unpaused, write down the coordinate vectors for each polynomial relative to the standard basis P2. So we got P1b, that's going to be 5, 0, 1. P2b is 0, 1, negative 4. And P3 sub b, the coordinate vector for P3, is 1, 1, negative 2. Okay, I'm going to put those vectors into a matrix and reduce it to determine if they form a basis. So we don't have to go to reduced echelon, we just have to go to echelon to look for pivots. And I'm going to let you do that on your own, but after a couple reductions, you should come up with 1, negative 4, negative 2, 0, 1, 1, 0, 0, negative 9. All right, that's in echelon form, pivot, pivot, pivot. So yes, these form a basis for R3 because we have a pivot in every row and a pivot in every column. That means the original polynomials, P1, P2, P3, form a basis of P2. So given that they do, and given that Q sub B is negative 2, 0, 1, find Q. So what we do there is we say Q is negative 2 P1 plus 0 P2 plus 1 P3. So that's negative 2 P1, I have to go up to the top and look at P1 it's 5 plus T squared. And then I'm going to add on P3, 1 plus T minus 2T squared. All right, and then combine like terms, and we get negative 9 plus T minus 4T squared. And that's it. Okay. that's a wrap. Do the rest of the problems. Solutions are at the end. Let me know if you have any questions.